Hello everyone, Gabe here from Ubisoft, and I'm here with Captain Smart. How are you today?
Am I captain now?
Yeah, you're Captain Smart. You've been promoted.
Nice.
I don't remember what you were last time, but you've been promoted to Captain.
Happy with that?
Yeah. How's it going?
Good.
What are we doing today?
We're gonna look at RAM, this first episode, but we're gonna do it in a little bit of a different way. So let's get excited.
Let's get excited. Get smart.
So, Gabe, we're gonna talk about RAM, but there is a certain thing we need to talk about first. And that question is, why?
Why?
Why do we need RAM? What is that? Like, we take things for granted. And like in the first CPU episode, we said, why do we need a CPU?
Yeah.
Well, we want to compute something. We want to do math. Math is fun. And in kind of the same way, what is RAM? Why do we need it? So my first question might be just, what is information? What is that?
Zeros and ones.
Zeros and ones?
I know that.
Is that? I mean,
well, within a computer it is.
in a computer, yeah. But if someone says like, oh, we have some new information, it's just knowledge, right?
Yeah.
Like a statement of fact or something. But then you might also ask you, what is data?
Zeros and ones.
Could be, yeah. Is information made from data?
Yes.
Or is data made from information? Like, where's this coming from?
Is this like the chicken and the egg?
Could be. So usually what people talk about is that information is processed to data.
Okay.
So in that sense, I can say, what is this?
That's a number.
It's a number. What number is that?
I believe that's 4.
That's 4. How do you know that?
Because someone told me it was 4.
Yeah.
That symbol means 4 when I was younger.
Little Gabe
Yeah.
asking teacher, what's this? And teacher says, this is 4.
Teacher told me to be quiet most of the time.
Most of the time,
Yeah.
I can imagine.
Sometimes
so
he said 4.
you would draw a 4,
Yeah.
and then you would say, how many sheep are these? These are 4. So we're taught that this means 4. But that's a symbol for 4.
Yeah.
What's this?
The meaning to life.
Meaning to life,
Yeah.
some might say. What number is that?
That's 42.
Really?
Or it's 4 and a 2.
Exactly.
Yeah.
Is that a 4 and a 2 or a 42? So if I represent 4 like this, it's 4 dots, so it's 4 abstract things. What is this?
That's 6 dots.
6 dots.
6 small circles.
6 small circles. Oh wait, is that 42?
It is.
So you can think of data and information with, there's a certain idea you can apply here, which is it's us that have to interpret it. Data, or just values out there in the wild, have absolutely no meaning until we say this is something. So when I said,
Such a sad existence for data.
yeah, well,
Just, you have no meaning.
you have no meaning unless, like, well, you have the meaning that I put into it. So is the 4 the health we have in the game, or is it the number of 1-ups that we collected, or is it the X position in the game? It is all of these, and it's none of these kind of thing. So this is a 6, or is this a 4 and a 2?
Which reminds me of electrons.
Yeah.
They're everywhere and nowhere at the same time.
Exactly. So when we think about numbers and data and that kind of thing, they're very abstract, and they can mean whatever. It is us that have to apply the meaning to it. So a little bit existentialism here. So what's this?
It's a 1 and 2 eyes.
1 and 2 eyes.
2 eyeballs.
Is this a number?
I mean, it could be.
What number do you think this is?
I mean, it looks like 100, but
Yeah.
I don't know of any zeros with a dot in the middle of it.
Well, it's just the font that does that.
Okay.
Yeah, but
It's 100.
100, or is it the binary system?
It could be.
Yeah. So where if there's a 1 in that place, that means
It's a 4.
it's a 4 in this case. So what is this?
Now it's just 110.
110. What does that mean?
It's 110 or something else in binary.
In binary, this is a 6.
Okay.
Could this be a 42 as well? Could we again be playing on this? It's a 4 and a 2, which means 42.
Could it?
Well, we could just make the system work that way. That just then means that there are a bunch of numbers that we can't represent.
But binary doesn't have a set value.
Well, binary works in this way that this is a 6.
Yeah.
Because you say you add up all the places that have a 1 in it. So it's 4 plus 2, that means it's a 6. If you want to make a 5, it's 1, 0, 1.
But don't certain combinations of ones and zeros have certain predetermined values?
Again, we go back to the thing. It's just they do that because we said so. Someone sat down and said, this is how it's going to work. So, what's this?
That's 1, 1, 1.
1, 1, 1. Or 4 plus 2 plus 1.
Yeah.
So we have a 7.
Yeah.
Okay, how do we do 8?
We add another 1.
Where's that coming from? In this world, there's no space, right?
Yeah.
So, again, you just add another 1. So an 8 would be 1, 0, 0. And then the highest number here would be 15. Quick math.
Yeah. What?
But it's 16 minus 1.
Okay.
Because the next number will be 16.
Yeah.
Okay. So we can represent numbers with zeros and ones. Here we could make any number from 0 to 15. So that works. We just have to put the 1 in the correct location. That's great. Would this work? So these are two numbers. Is this 42?
No, because you're changing the zeros and ones, but still assigning the same value to them.
Yeah.
Like the 4 is a 1 in the left one, but it's a 0 in the right one.
So are these two separate numbers? Is this a 4 and a 2 separately? Or is this a 42?
I have absolutely no idea.
Again, we could have made a system where like that's what that means.
Okay.
That's fine. In computing, you'd usually have them like there's space isn't a thing. That's not an idea. Because you would just
We're
have
efficient.
Yeah, it's just things are just one after another, and these representations are just abstract representations. They don't actually mean anything because we have to apply the meaning. So this would work because this is a 4-bit computer. So we'd say we are making a 4-bit computer. We have 4 bits, which means the highest number we can represent is 15. And what that means is if we have a 4-bit computer, then one number is 4 of those bits. If we have a 8-bit computer, we would have it like this. We would go from 8 to 16, 32, 64, 128. So the highest number here is 255. Again, quick maths. So in this system, the same data, if you think of it that way, it's the same zeros and ones, mean different things just because we put meaning into them. So it also matters when you see a series of zeros and ones of data, whatever, you need to know the context, you need to know the environment in the system.
So when you have, if you go forward one more again,
Mm-hmm.
so when you have 128,
Yep.
are there 128 different things that could be 0? Or because to me this is still 8 zeros and ones.
Yes.
So
these are,
how is it storing different?
we're not thinking about storing it.
Okay.
We're just thinking about the idea of
Okay.
numbers and values. So if you wanted to represent the number 128, you would put 1 in that first place and then 0 everywhere else.
Okay.
If you wanted to represent this number, this is 66, you would do this. It's 1 in the second place and 1 in the second to last place. If you wanted to 67, it's 1, 0, 0, 0, 0, 1, 1. So we can represent every single
And if you
number.
wanted it to represent 3, you would just have 0, 0, 0, 0, 0, 1, 1.
Yeah.
Okay,
Yeah.
got it. I
But
speak computer now.
yeah, but it's in this system. This is an 8-bit value,
Yeah.
which means that all the 8 bits have a meaning together. If we would read this from some 4-bit system and read it as an 8-bit value, it wouldn't make sense.
Yeah.
It would still give us the same value.
But it would. But the 6 or the, what is it? 8-bit.
Hmm?
This is 4-bit.
4-bit, yeah, and
This is 8-bit. The 8-bit would assign different numbers, because this one, cheated. This one would still send in. This is sending in 6.
Yeah. Well, no, this is a 4, and then a 2.
Okay.
These are 2 separate values.
Okay. But if it sends in, if the 4-bit system sends in a 4 to the 8-bit system,
Mhm.
the 8-bit system's still gonna read it a 4, but
Yeah.
that 4 might not mean the same thing.
Yeah.
Okay.
Yeah. So it matters where you're storing it, and context that absolutely matters. So, and again, here we have 42.
Yeah.
It's great. So if you would see a streams of zeros and ones, if we look at it like this, it doesn't mean anything.
No. Is it always doing then in 8-bit system 8 zeros and ones at a time?
Yes.
Okay.
Yeah.
Okay.
So if we have a 32-bit system or 64-bit system, if you want to store the value 1 in a 64-bit system, you have 63 zeros and then a 1 at the end.
Yeah.
So you can think of like, oh, you're wasting a lot of...
And basically, the more bits you have, the more information you can store?
Yep.
Okay.
Yep.
What's the biggest information we have now?
The big number.
Big number?
Yeah. And again, these are just numbers. So if you want to store letters or something else...
When I think like my Windows operating is a 64-bit
Yeah.
operating system,
Yeah.
wouldn't it be faster if it was a infinite bit or like a 1 million bit?
It would store more data. I don't know if it would be faster. So you could store more things, but
Infinite bit.
if most of the things that you're storing are low numbers, like the ages of people, that's not a big number usually. It goes up to 100 or so.
That's a lot of zeros before you hit the ones at the end.
Yeah, so if you imagine them all one after another, there's a lot of zeros that are not doing anything.
Yeah.
So there has to be kind of this trade-off.
A balance.
Yeah, so when you're programming, you would say, I need these many bits to store it. And then this operating system and the language will help you with that. But you can then store up to 64 if you want. So, let's then imagine we want to store those zeros and ones in some sort of magic box. The question then becomes, how do you store a thing? How does it, you say, I want a thing to be there, and then you come back later and it's there. And
you assign a value to it.
Yeah, but how? Like,
I have no idea.
So now we're back into like electronics world a little bit. I'm not as versed in memory as in CPU, so but we'll have a little fun here. We want to store things like this, right? That we have those 4 bits. Most of them are 0. One of them has a 1 in it. So if someone would read from these magic boxes, they would get a 0 from all of them, or low voltage, or however we want to store that, and then a 1 or high voltage in one of them. So we want this magic box, right? And then we just want millions of them to have whatever gigabytes of memory we want to have. So let's then focus on one box, 1 bit, 1 0 or 1 1, where we can store it. We can send in a 1, and then it's stored 1. And if someone's reading, they would get
1 back.
1 back. And then if nobody's doing anything, it would just be there. It would just be waiting for you. So how would you do that? How would you store a 1? And there's a thing that's happening which isn't shown in the picture, or won't be shown, which is there's always voltage also going through these. So they have power, basically. So this sounds weird, right? So let's think about another kind of system. No? This is another system.
Okay.
Yeah, this is another system.
I recognized that for a second, and then you just shot down my dream.
So I'm sorry. So this is going back to the first CPU episode. So let's think about a system that already exists. That if I send in 2 zeros into the system, I get a 1. Okay. If I send in anything else, 0 and 1, 1 and 0, or 1 and 1, I always get 0. So they have to be 2 zeros coming in, and then I get a 1. Okay? So that's great. This is called a NOR gate. A not OR gate. An OR is if any of the values have a value, you have a 1. But this is a flipped version of that. Okay? So here's a cool trick that you can do with an OR gate. So let's imagine a system. Let's build a little system. We want the system that we can say, I would like to set the value of this magic box to 1. I don't know what the value is now, but I want it to be 1. Great. I also want to say, I would like to set the value of the box to 0, and then whatever is the result in the box. Okay? Sounds good? So if I say, I want to set it to 1, I don't want to set it to 0, and then in the box is a 1. So it's like I'm pushing, if imagine these as 2 buttons, I'm pressing one of the button, I want it set to 1, and then it's 1. Because then, if I let go of the button, so it's a 0 in both, it stays a 1.
Yep.
It's like, I flip the switch, it sets it to on, I'm not flipping the switch anymore, but it's still a 1, it's still on.
But is that because you've had it set to 0, on 0?
Think of putting a 1 in the first column as the action that you want to do.
Yep.
And then sending in 2 zeros into both means that you don't want either.
Oh, okay. So then to set it to 0, you would put a 1 in the 0.
Yeah. So if you
Okay.
say set to 0, you say 1 there, now that there is 0, and then if you let go, or 0, 0 in both, the 0 is still there.
Yeah.
Isn't this remembering, right?
Yeah.
So this is an idea of, it remembers, here's an action that's happening, and then the result data is changed, and now there's no action happening if you think of it that way, but the data remembers what was the last one. And then there's an action happening, it changes, we go back, it remembers.
Yeah.
Right? So this would work, right?
Yeah.
Cool. So let's build this kind of system. And this
Okay.
might get a little tricky, but stay with me. So let's use 2 NOR gates. Remember, NOR gate has 2 inputs and 1 output. So of course, here's the gate,
Yeah.
here's the table. If you have an A and B, it's called Q usually, for status quo. Don't know, don't ask.
Okay.
So you have an A and B input,
Yeah.
and then it's only if both of the inputs are 0, we have a
Then-
1.
Okay.
Whatever else happens, it's always a 0.
Yep.
So that's an easy enough to get through. So we have the 2 inputs and outputs, or not. Wait, why don't we have 2 inputs and outputs? We'll get to that. So they are called, so R is called the reset. And that's we want to go back to 0. S is to set, we want to go to 1. Q is the output, that's the one we read, that's the actual memory. And Q dash or Q marked, that is the opposite of Q. That's just the system happens to also give you the opposite of what's in there. But anyway, but where are the other ones coming from? Because a NOR gate needs 2 inputs.
I have no idea.
What would be the weird thing to do here?
Something that's already in there.
Something else already in there?
Make it spawn magically.
Spawn magically.
Yeah,
Well-
that'd be weird.
We like magic, right?
Yeah.
What about this?
What the?
So the output
Ah.
of one of them is the input to the other one.
Okay.
So we go from the S output, the Q dash.
Is it just assumed that the S gets the other input from somewhere? Oh my god, what
Yeah.
is even happening?
Yeah,
That's just an infinite loop.
this is a loop, exactly.
Ah.
So they are reliant on each other.
Okay.
So
But you can change basically the value still in each gate by changing R and S.
yes.
Okay.
Okay, so let's imagine that we're going to use this system. Let's imagine that we have 2 NOR gates, we put them in some sort of electrical system, connect power to it, and then connect it like
Won't
this.
you eventually though end up with 0 all the time in this?
No.
No.
Yeah.
Because as soon as you send a 0 in on one of them, it's going to be sending a 0 in to the other one, and then it's just 0, 0, 0 over and over because it,
So
or a 1. Yeah, actually.
there's a thing you can't do. You can't send in 1 on both R and S.
Okay.
That's not allowed in the
I just
system.
realized I was confusing 1 and 0 somehow. I had managed to confuse a 1 or a 0.
Yeah.
Because you have to send in 0 twice
Mhm.
to get a 1.
Yeah.
Not send in 2 1s to get a 0.
Yeah, so the only way to get a 1
Yeah.
is if both of them are 0.
Which will happen quite often.
So let's go through this.
Or somewhat often.
Yeah, let's go through this step by step. So let's say that we want to send in a 1 here.
Yep.
We want to do a set. This is from the table in earlier slides. We want to store in the system a 1. So it's a set 1. We want basically we want 1 out of Q. So that means that we get a 0 out of here because if there's a 1 in S,
It's always going to be a 0.
it's always going to be 0, like the table shows, that it doesn't matter what's coming from Q up there.
Yeah.
It can be a 1 or a 0, it doesn't matter, we're going to get a 0 out. Which means that there's a 0 in here.
Coming into the other one.
Yeah, which means that in R, because we weren't resetting it, we were only setting it, R is 0, like from the table, we want to set,
Then we get a 1.
we get a 1.
Okay.
Cool, so this which then means goes around, and we get a 1 here, but it didn't actually matter, because we get a 0 out anyway.
But where's the S and the R coming from?
Us.
Okay, so that's okay.
We are controlling the system.
okay.
Yeah. So we have this little loop here going on. Great. So now what happens if we set S? So we have, this is the world right now.
Yeah.
This is the setup.
Yeah.
Yeah. We now send 0 to S.
Okay.
So we send 0 to S, which means it's a 1 and a 0.
Which means you get a 0.
So there's nothing changed, right?
Yeah. It just sends it back. But R is still a 0?
Yeah, because we were backed off.
Okay.
If you imagine the table from
Yeah,
before.
so then you get an R out, or 0 out in Q.
Yeah. Isn't that the thing we wanted? So if we go back here again, we want it to store 1 in the system. It did all this thing, and now we got a 1 out of Q, 1 not there, great. And now we don't give voltage to S anymore, or send a low voltage, or we do nothing, and nothing changes. Didn't we then store? So now we're sending a 0 and a 0 to R and S.
Yeah.
But Q is still saying 1.
That's right? It's wrong.
No.
Why is it saying 1?
It's correct. If you follow. So there's a 1 and a 0 in S.
Yeah.
1 and a 0 gives a 0 out.
Yeah.
That's still correct. Which means that 0 goes up to R.
Yeah.
We aren't resetting. So there's a 0 in R. Which means that if you have a 0 and 0, we get 1 out.
Okay. Yeah. Okay. Yeah. Got it. Yeah.
So it's
just because S isn't sending anything new.
Yeah.
So it's still holding the same value, which was 0 before.
Yeah. So it remembers what we did before. So if we want to reset, let's say we want to reset, then we send the 1 and a 0 into the top one, which means that Q is 0.
Yeah.
Which means that a 0 goes down to the lower NOR.
Yeah.
Which means it's a 0 and a 0.
And now
means 1 out, and then 1 back up there.
Yeah.
Doesn't matter. And then we release. It's a 0. It remembers it.
What's the practical use for this? Where do we?
This is RAM.
What?
Yes. This is SRAM.
That's how RAM works?
Yeah. You
Okay.
set a 1 or you set a 0,
Okay.
and then you stop setting a value in it, and it remembers it because you have this loop going on.
Okay. So this is what it's constantly doing with information, non-stop.
Oh,
We-
so fast.
So fast.
So
So
fast.
fast.
So these are expensive to make.
Okay.
So these are usually used in SRAM kind of situations.
What is SRAM?
That's usually in cache. It's used on older machines. If you
Okay.
want to have a really small cache, you make it our SRAM.
Is this what goes into the CPU?
Yeah, and a lot of chips make these.
Okay.
And they can make these really tiny.
What is RAM that we use in like my 16 gigs Corsair DDR4
So
RAM?
those are capacitors.
Okay.
So you would then fill the capacitor with value, and then after a few milliseconds or nanoseconds or whatever, they slowly fade. So you have to keep refreshing them.
So how much faster is SRAM compared to?
Way faster.
So are we eventually just going to see SRAM everywhere?
No.
That's disappointing.
There might be other things coming out. There's a thing called the memoristor, which is being experimented on, which are really tiny and fast. But yeah, so we have this box now.
Yep.
We're happy. So then we can think of this as a magic box where if I send the 1 into the set value, 1 is stored into it, and then I back off, we still have a 1 in there. So if I'm reading, I get a 1. If I send 1 into the reset, I get a 0 in it, and then I back off.
Yep. And now you're back at 0.
Yeah. There
Nice.
we go. So this is called an SR flip-flop.
Senior flip-flop.
Yeah, it's a set reset flip-flop.
Senior flip-flop.
Senior flip-flop. So yeah, these are in a lot of chips. This is one way of doing it. There are many other ways of doing like these loops and things, and they have their advantages and disadvantages and all that kind of stuff. And we have talked about it. Almost sounds like they're instant, where you do it immediately. Electronics don't work that way. There's always a little bit of time before when you say, like, I want to set it, and when you can safely read from it. And that's a lot of the timings that people talk about. Yeah. In DRAM, the timings are longer also because you have the capacitors and that kind of stuff. So you have
So you have like CL16 and CL18.
Yeah, I think that applies more to capacitor RAM, but in these it's not a binary system. There is a certain kind of build up.
But even with the time you're talking about, this is like,
Oh, this is very minuscule.
okay,
But
but minuscule in the sense that this is not perceivable.
no, but if you're building systems that rely on it,
Yeah.
you might hit that little boundary time where you actually get the wrong value. So you want to guarantee that, and usually these are running on clocks as well. So there's a clock cycle, and then you're not allowed to read until the next clock cycle. And these can be on the same clock cycle as the CPU or on its own clock cycle. That's often more common that they have their own. Yeah. So
RAM.
Suddenly RAM.
Suddenly RAM.
Yeah.
So now we're on a RAM adventure.
We're on a little bit of RAM adventure. So this was kind of a more low level,
fundamental look
Yeah.
at like how.
like first of all, what is data, and then also how can we just store a thing, like a thing happened in the past. How can we use electronics to then remember a thing we did in the past? So this is one way, and I totally recommend looking into. If you Google flip flops, you get a lot of
A lot of sandals.
sandals and a lot of memory, basically.
So what are we doing next time?
So next time it's more programmery and more. We're going to mention more stuff that you might hear in everyday terms. And in one of the CPU episodes, we talked about how we might avoid or lessen some of the loading time, the time it takes to load things. And I'll show a little bit how that's done.
Sweet. Well, until next time, everybody, stay smart.
Huh?
Bye.